Hey, Alyse.
Andrew.
Did you want this one recorded? I wasn't sure what Andrew picked.
Oh, yes, that would be great.
Okay, excellent.
And just to check, Andrew, are you seeing the full presentation?
Yep, looks great.
Great, thanks.
Let's give it maybe another minute, Alyse, and then I can introduce you. I don't think Andrew's gonna be able to join, right?
Yeah, that's right, and sounds good.
Okay. Okay, why don't we go ahead and get started? Thank you everyone for attending another BBSR seminar series. Today, Alyse Staley is going to be talking about data cleaning in our Tidyverse. And next month, Eric Clamby will be talking about something flow cytometry related. So, okay, Alyse, why don't you go ahead and get started?
Great, thanks, Andrew. Today I'll be talking about data cleaning using the R Tidyverse. As an overview, today I'll first discuss what clean data are, as well as why you should be using R or a different data cleaning software, as opposed to something like Excel. I'll then introduce the R Tidyverse itself, including comparing it with base R, how to load data and packages into R, and some useful syntax used in the Tidyverse. I'll then get into the primary part of the lecture, which is to introduce some select Tidyverse functions. For each function, I'll provide its purpose, a simple example, and in some cases, examples of how the function can be extended to more complex situations. I'll then briefly go over some general coding tips so you can be more successful with the Tidyverse, and we'll end with a brief summary and some additional resources that you can use as you learn the Tidyverse. Starting with clean data. As a brief overview, tidy data sets are all alike, but every messy data set is messy in its own way. This can be thought of very briefly for tidy data, as every column is a variable, every row in your data set is an observation, and every cell is one single value. To illustrate the difference between clean and messy data, here's a table with a few examples comparing the two. For example, messy data may have variable names that either start with special characters and are overly long, or conversely are uninformative names. In contrast, clean or tidy data uses short and meaningful variable names. Messy data may also have special characters that interfere with the statistical analysis. For example, you may have commas in numeric variables. Additionally, variables may be stored in the wrong format. So a variable that should be numeric may be stored as a text or character. In tidy data, on the other hand, variables are already ready to be used for statistical analysis, and that data type is appropriate for the analysis you want to do. Messy data may have a lot of other problems as well. For example, there might be duplicate rows as opposed to one row per observational unit. And in character variables, there may be issues with inconsistent spelling of the same category. Tidy data, on the other hand, is free from these errors. Another example of messy data has to do with missing data. For example, you may have zeros or blanks instead of missing values, whereas tidy data has a consistent missing data structure throughout the entire data set. Now, why is it important that we transform messy data into clean data? First, clean data are an important part of reproducible research. If our data are clean, we can use the highest quality information available for our analyses. If we use messy data, we may get incorrect results, which can be thought of with the idiom, garbage in, garbage out. In other words, if we use a messy data set to perform our analysis, our conclusions are also going to be messy. Additionally, clean data help keep the project organized and consistent, and that helps to increase productivity. With data cleaning in the broader context, data cleaning is the first step to every analysis. Once the data are clean, their quality should then be examined. And this includes looking at the distributions of each continuous variable, examining outliers, or for categorical variables, identifying the number of observations per group. It also involves looking at the bivariate relationships across variables. If you're interested in this step, a previous BBSR lecture, Improving Efficiency with R, goes into this. And finally, once the data are clean and the data quality is considered good, you can go ahead with a statistical analysis. But today, we're just focusing on step one, getting clean and tidy data. At first, it may seem easiest to perform your data cleaning steps in a program such as Excel. However, this will likely create a lot of problems in the long run. To start, Excel is point and click. That means that there's no record of the data cleaning steps that you take. This first means that the research is not fully reproducible. It's really easy to make mistakes, and it's also inefficient. You may be asked to make a small requested change, for example, to your data set. And in order to update your data set, you may have to go all the way back to the very beginning to try to remember every step. However, if you use R or a different programming language, you can just alter the line of code, and it's completely documented and reproducible. So what should you do instead? Excel can be used to store data sets. This is also something like REDCap or another database can come in handy for. The best practices are then to save the original file as raw data. This can include naming it as such and keeping it in its own folder. Then this raw data file should never be altered, and it can be helpful to save it as a read-only file. The next step is then to use a coding language, whether that be R or a different language, to manipulate the data. Once the data is clean or processed, you can then save a separate process data set with a new name and perhaps in its own folder. And this process data set can then be used for all your downstream analyses. Now that we've briefly addressed what clean data are, I'm going to transition into our Tidyverse itself. Base R are functions that are included in the R software when you install R on your computer. Since R is an open source software, anyone can publish packages or sets of code that you can then load into R. The Tidyverse is an example of this, where it contains a series of different packages. Today's presentation focuses on two of those packages in the Tidyverse, tidyr and dplyr, which are used for tidying and manipulating the data. To compare the Tidyverse to base-R, first, one of the biggest attributes of the Tidyverse is that it uses a consistent ecosystem of code. In other words, once you learn the structure, you can then learn new Tidyverse functions really quickly. Additionally, Tidyverse functions are much more readable than base-R. For example, you have a Tidyverse function that is used for columns and another one that's used for rows. Whereas in base-R, you have to basically be using X and Y coordinates to achieve this. Additionally, R has many nuances that take longer to learn. Certainly not everyone will agree with me, but I think it's a lot easier to learn to code in the Tidyverse than with base-R, at least to start. And finally, especially when you're learning, keep in mind that if your base-R code is working, then go ahead and use it. The idea behind knowing more functions is that the more tools you have, the better you'll be at problem solving. Personally, I use the Tidyverse for nearly everything, but there are certain situations or cases when the Tidyverse tools just aren't working for me. And in that case, I'll fall back on base-R. In order to use the Tidyverse functions, you first have to understand how to load packages into R. If it's your first time using the Tidyverse, you need to install it. You can either install the entire Tidyverse. This is what I prefer to do because I use most of the packages that are included in the Tidyverse, or you can just install the ones that you need. You only have to install packages the first time you use them, but then every other time that you create a new script, you have to load those packages into R. For the Tidyverse, you could just use library and the entire Tidyverse, or again, you could load specific packages. It's also important to know how to get your data into R to start. So the first thing you have to do is set your working directory, and that's the location where your raw data are stored. And then you can use one line of code to then import the data from that working directory. If it's a CSV file, the read.csv does just fine. Transitioning into the syntax you need. The first really important concept of the Tidyverse is what's called piping, which is designated by these symbols here. Pipes are used to apply a sequence of steps or functions to a single object. For example, this is a data frame iris, and then you can see there's a piping operator after iris. This means that each of these functions is applied to the iris dataset in that order. Group by, summarize if, ungroup, etc. are all applied to iris. This example also shows the clearest syntax for using pipes. Each function should be on its own line, and in the case where you have a lot of things you're specifying for a function, it may be helpful to have each argument on its own line. You want to avoid something like this, where everything's bunched together and it's a lot harder to read or review your code later. Additionally, it's important to understand how to assign objects, which is done with the arrow operator in R. If you want to view a change without updating an object, you can simply apply a function. So we're piping it and then using it here, but you're not using an arrow operator. So you're going to view the change, but you're not going to actually update the data set. If you want to update the data set, you can do so by specifying the same name of the data set. If you want to create a new object, then you're creating a new data set, in this case called new.data, that is taking your old data set and then applying the change. It's also important to keep some logical operators in mind. This is especially helpful when you're trying to decide which rows in your data set you want to keep. Some of these operators are pretty standard, such as the less than or equal to, as well as greater than or greater than equal to. When you're using equal, you're using this exactly equal or equivalent to, and you have to actually use two equal signs in a row. It's also helpful to understand that the exclamation mark operator is used to negate. So instead of saying equal, you're saying not equal to. And finally, the or and operators are also helpful. Now that we've introduced the basics of the Tidyverse, I'm now going to go into the primary part of today's lecture and start discussing some of the many Tidyverse functions available. To start, the rename function is very helpful in changing variable or column names. At the top, we have an example dataset called Iris, and I'll be using this as an example dataset throughout the introduction of the various functions. In this dataset, we have a bunch of different variables, one of which is sepal length. So this is all about the flowers here. Let's say, however, that I don't like the format of this variable name. I can update Iris with the assigning arrow operator, take Iris from before and the pipe, because we're going to apply the function, and then I'm going to use rename. So rename, new name equals old name. And if we print it, we can see that sepal length has now been updated to our new format. An extension of the rename function is the clean names function from the janitor package. So note, this is actually not from the Tidyverse, but it still uses the piping and is a useful addition to your Tidyverse functions. Let's say we received data from an investigator that was not in a format that's very compatible with R. So you can see these aren't great variable names because they start with numbers and also have spaces separating the words as opposed to underscores or periods. We can load the janitor package, and remember, you would need to install it if you've never used it before. And we're going to take this bad variable name data and simply say clean names. And now it will go ahead and return variable names that are already in the usable R formats. If I have a really messy data set, I like to start with this function, and then I can go ahead and tweak it with the rename function later. Next, it's important in your data set to be able to select which rows or variables that you want in your data set. And this can always be done with the select function in the Tidyverse. Again, we have an example of our Iris data set. And now we can go ahead and select the variables that we want. So sepal length and species in this case. And that is now printed in our data set here. Select has a lot of extensions, and I'm just going to go over a couple here. To start, we can use operators that take a look at the beginning or the end of the word. For example, we can select words that start with the pedal term, or, so that's our or operator, ends with the with term. So now we have all the variables that meet either of those criteria, right? So pedal length, pedal width, and sepal width. Similarly, we can do the same thing, but instead of or, we can say and use the not operator. So we don't want it to end with width. And that's just going to leave us with pedal length. In addition to being able to select the columns, it's also very helpful to be able to decide which rows or observations to retain based on a series of criteria. We again start with the iris data frame, and then we want to filter it or only take rows where petal length is less than 5. And so we can see here, if we look at petal length, there's one observation that's greater than 5, and we go down here, and that has been eliminated from our data set. We can also filter by multiple criteria at once. So maybe we're going to filter based on the species, and we want petal width to be exactly 1. And here it is retained for us. The next primary function is mutate. What this function does is it can either create new columns or variables based on existing variables, or it can update or modify existing columns. Starting with the iris dataset, let's say we need a variable that multiplies the length and width of the sepal. So we have sepal.l.w equals sepal length times sepal width. And let's say we're also interested in taking the log of the petal length. This then creates two new variables with the names that we specified that then perform the functions for us. Right, so sepal length and sepal width, 7.3 times 2.9 is going to get us 21.2. Like all these functions, there's a lot of extensions, but just a few of them for mutate is that we can change all the variable types in our data set at once. For example, this mutate if looks through all the variables in your data set and says, if it is a factor, so is.factor, then it will change it to a character variable. Likewise, we can use this across in matches. So matches sepal. That means any variable name that contains the word sepal. We are then going to perform the mutate action of log transforming. And you can see here that the sepal variables were log transformed, whereas the length variables, as you can see from above, were not. It's also helpful, especially for creating tables and other kinds of presentations of your data, to be able to sort your observations or rows by given column values. This can be done with the arrange function. So if we arrange by sepal length, then we are going from smallest to largest sepal length. We can also sort in reverse order with the descending function, and we can order by multiple variables at once. Since in this case, we're specifying species first and then sepal length, it's going to first go by species, and then within the same species, that's where it will order by sepal length. The next aspect of messy data is a lot of times there are issues with missing values. The first function I'll introduce to address this is the drop NA function, which removes rows containing NA or missing values. Here's an example data set where you can see we have X variable and Y variable. X has one missing variable in the third row, and Y has one missing variable in the second row. If we want to remove all of the NA values in the entire data set, we can simply use drop NA, and you can see this is only left with our complete cases, in other words, not missing X and not missing Y. We can also use this function to remove missing variables in a specific column. So in this case, we're removing X values, drop NA of X, and you can see missing values in Y are still retained. The next function is the replace NA function, and this can change NA to any other value. So here we have replace NA, Y equals unknown. That means that any NA values in the Y column, we can change to the word unknown. However, more likely than not, that's not actually what you want to do. Instead, you would rather have data that comes to you messy. In other words, it's not using consistent structures for missing data. And you want to change this unknown value to NA. This can be done with NA if. This is saying that any value that's written as unknown in the entire data set, we can change to NA. And that can be seen right here. Next, it may also be helpful to summarize your data. This can be done by combining the group by and the summarize functions. First, you have to set the grouping level, and then you can retain those summary statistics at that level. For example, going back to our iris data frame, we want to get summary statistics at the species level. So that's going to be what we're going to group. And then we want to know what's the mean petal width, what's the standard deviation of the petal width, and what are the number of observations, all by species. You can see here for the n.species, this is another function in R. We're just going to pull out the number of rows for us with this n function. This very nicely gives us an output table where we can see there are exactly 50 observations for each species, and there's a mean and standard deviation provided in each of those groups. Now I'll transition into some of the more complex functions in the Tidyverse. Pivoting is really useful, but does take a little bit of a learning curve to figure out how to best reshape your data. So what pivoting can do is it can reshape your data either from long format to wide format, so using pivot wider, or conversely from wide format to long format using pivot longer. Here's an example of long format where, simply put, you can see that the values in the first column repeat. Whereas in wide format, each of those values in the first column is unique. Each format may be useful for different kinds of analyses. For example, long format may be really helpful when you're doing a longitudinal data analysis. For example, you might want a row for every single time point, and then your values could be the values that occur at those specific time points. Whereas if you're using a cross-sectional study, you may want to perform a regression analysis where you're adjusting for multiple variables in your data set. And in that case, the wide format is what you would need to perform that analysis. This can be illustrated here. Starting with a subset of the iris dataset, we're going to take this from its relatively wide format, so take it from its relatively wide format and transform it into long format. This is done again through the pivot longer function. Calls is our first thing we need to specify, which is specifying which columns we want to take from wide to long. In this case, it's going to be sepal width and sepal length. Then we need a new column for what we're going to put its names to. So in other words, where sepal width and sepal length will be stored. And another name of the variable that we're going to use to put the values or individual numerical observations in this example. This can be illustrated here, where location specifies width or length, and our measurement is then presented in its own column. If we want to take this long format and bring it back to a wide format, we have to use pivot wider, specify where the names are from, and where the values are from. So our names are going to come from location, our values from measurement, and we can get back to our original data set. Next, it may be helpful to combine multiple data frames. For example, your clinical data may be in one data set, and your lab data may be in another. The first option to combine this is with the full join function. This keeps all the observations in both of your data sets. In this case, we'll call our data sets X and Y. What this means is if you're joining by an ID column, you're going to have all of the IDs in your data set that are present in data set X, are present in data set Y, or are present in both data set X and Y. What this means is it may induce some NA values. In other words, if you have an ID that's only present in your X data set and it's absent from the Y, then you're going to have that ID in your data set. You're going to have all of your X values, but then all of your Y data set values are going to be missing. To avoid this, you can use different kinds of joins. However, you have to be really careful with them because they do remove observations. Inner join keeps observations that are available in both X and Y. Left join keeps all the observations that are available only in your first data set here, and right join in your second. I really suggest if you're new to coding in general or to R specifically, that you just stick with full join. That's because it's really easy to accidentally remove observations if you're not very careful about how you use these different joins. You can always start with full join and then remove those NA values as a secondary step. Understanding joining is a bit easier to understand with an example. Here's some default R packages. Band members have the name of a musician and the band they belong to, and band instruments have the name of the musician and what instrument they play. We can create one joint data set called band by combining band members, first data set, and our second data set, band instruments. So in our previous examples, this would be X and this would be Y. And we want to specify what we're joining by, which in this case would be the name. Then you can see there's a few different combinations of how this turned out. For example, for John and Paul from the Beatles, we know that they play guitar and bass. That's because they were available in both data sets, and so we have no missingness. But if you look at Nick from the Stones, we know his name and band, but he wasn't included in the band instruments data set, so we don't know what he plays. Likewise, Keith, we know from the band instruments that he plays guitar, but he was missing from the band members data set. So from this data set, we don't know what band he belonged to. And finally, as a reminder, we can put it all together with piping. So if we start with this iris data set, we can select the variables we want, then filter to a specific species, and then we can go ahead and make some transformations with Mutate. So we can create a new variable called log of sepal length, and finally we can sort it in log of sepal length. And now we can go ahead and return a data set that's performed all those steps clearly and efficiently at once. And this is something you can build up to. As you're learning, I suggest just applying one function at once and checking it as you go. But as you get more comfortable with the functions, this saves a lot of time to be able to pipe commonly used ones together. Now that I've introduced just a handful of the functions that the Tidyverse has to offer, I'll now transition into some basic coding tips that can hopefully make you more successful as you learn to use the Tidyverse. Firstly, it's always important to ask yourself, does this make sense? As I alluded to in the last slide, you should always check your data frame after applying each function. That way you can double check that the function you're using is doing what you intended. It's also always good to check your work in multiple ways. For example, you can look at a plot or table of the distribution of one or two variables, and you can make sure your numeric variables add up correctly. Another really important thing is that if your code isn't running in R or in the Tidyverse, you will usually get an error message that will attempt to tell you what went wrong. But those error messages aren't always clear if you're unfamiliar with them. And so you can copy and paste the entire error message and Google it. And more often than not, if you've had the issue, it's likely that someone else has too. And chat groups like Stack Overflow will often explain how to resolve exactly your problem, or at the very least, point you in the right direction so that you know kind of the next steps onto how to solve your coding problems. Another disadvantage of an open source packages, such as R and others, is that you may have packages that interfere with each other. What's happening is that R may think a function is from a different package than you intended. For example, maybe you meant to select from the Tidyverse, but there's another select function from a different package that you have loaded. This is a really common problem, and in my experience, whenever my code isn't working, this is by far the #1 cause of the problem. Luckily, this can be resolved pretty easily by specifying which package you mean. You can simply write the package, 2 colons, and your intended function. I'll now briefly go over a summary and point you to some resources that can help you with coding a lot more than just today's introduction can provide. In summary, reproducible data should be manipulated with code as opposed to a point-and-click software such as Excel. And one of the easier ways to do this is with the Tidyverse, which is a consistent thought of ecosystem of R packages that provide tools to both clean and tidy your data. Today I introduced just a few key functions that can be performed on a single object through the piping operator. And this is really just the beginning of what the Tidyverse has to offer. To start, the Tidyverse package has really helpful documentation, some of the best I've seen out there for our packages. It includes information on each package in the Tidyverse and also really detailed information on each function in the package. It also includes many, many more functions and extensions to functions than I introduced today. Here's an example of what you might find when you go ahead onto the resources page. If you go on to Tidyverse dplyr, you can see that there's a nice overview and also some vignettes or very detailed tutorials with our code that's ready to use and to practice with. The other thing that you have to check out on the website is that each package, such as dplyr, has cheat sheets that are available. And these are very useful to remind you of the available functions and how to use them. As you can see, they also have some nice visual reminders as to how to go about these functions. And finally, today's lecture will also be available on the Cancer Center's YouTube page. So I encourage you to go check that out and hopefully can use these slides as a resource to you as well. Today's talk was put on by the Biostatistics and Bioinformatics shared resource, and our Biostatistics core can help you with any kind of biostatistical analysis, study design, or manuscript assistance. We're really happy to help you with any of your projects, so please feel free to reach out to us. Thank you for listening today, and I'll now open it up to any questions.
Thank you, Alyse. As a base R user, mostly, that was definitely helpful. It'd probably take a lot for me to change all the functions I use to incorporate that, but I definitely should be, I think. There are a couple of questions in chat. Can you open that on your end?
Oh, sure. I sure can.
Okay.
Can you save or export a data set as read-only in R? I don't know the answer to that question. That would be cool if that's possible. I don't know, Andrew, have you ever heard of that?
I don't know the answer to that, but there are packages where you can export like data frames as Excel files. And I know you can set a lot of the features in Excel, like such as like highlighting columns or bolding text and things like that. So it's possible, but I don't know if you can actually do the read-only option there.
Yeah. The next question I got was about compatibility for SAS and R. So I want to translate my SAS code into R in order to have perform cleaning and transformation of the data, in which a lecture would be helpful. I know there are certainly books out there that's like learning R for SAS users, something of that nature. So I can find out what that is and send it. I don't know of specific lectures, but yes, that's certainly a topic that I know a lot of people run into as they're trying to convert between them. But I'll send the book. At least hopefully that it can help a bit. Kristen asked, can you explain what a tibble is and how it differs from a data frame? Are there repercussions about going back and forth? So a tibble is just a nice way to be able to display a data frame. And I don't have any issues going back and forth. Honestly, it's a nice way to present for a lecture so you can actually see the data frame well. I usually won't convert my data frames to a table personally, and then we'll use something like flex table to make nice tables later. But that's a preference. A lot of people really do like tables and don't have a lot of issues converting.
Just a quick comment on that. I had some issues. I think that the table would, I don't know, lose some, I think it was row names or something. So if you convert back and forth, you might have to save them somewhere separately and then add them on.
Oh, thank you. That's really helpful to keep in mind. Yeah, row names can certainly be tricky in R. Personally, if I'm using row names, in a lot of cases, if I'm using row names that aren't just numeric 1, 2, 3, 4, I will create a new variable that has that row name as well. So like maybe ID or something, and I use the mutate function to do that, just for exactly what Thomas brought up, that can, yeah, row names create a lot of issues also when you're converting to matrices.
Okay, are there any other questions for Alyse? I'm glad we got a few. Thank you very much, Alyse, for giving this talk. That's very helpful. Yep, next month will be Eric Clanby, and yep, if there's nothing else, then I think we can end this. And thanks again, Alyse.
Yeah, thank you, Andrew.
Bye, everyone.